Multiple processor sharding. CPU sharding is more complex when multiple CPUs are available. We consider the processors are identical. We call it homogeneous within a multiprocessor system in terms of their functionality. We can use any available processor to run any process in the queue. But we also have to consider load sharing. If we provide a separate queue for each processor, maybe one processor is idle, one is busy. Limitation. Consider a system with an I/O device attached to a private bus of one processor. Processes that wish to use that device must be scheduled to run on that processor. The first section approaches to multiple processor sharding. One approach to CPU sharding in a multiprocessor system has all sharding decisions, I/O processing, and other system activities handled by a single processor, the master server. The other processors execute only user code. This we call it a symmetric multiprocessing. It's simple because only one processor accesses the system data structure, reducing the need for data sharing. A second approach uses symmetric multiprocessing. Symmetric multiprocessing, where each processor is self-sharding. All processes may be in a common ready queue, or each processor may have its own private queue of ready processes. Regardless, sharding proceeds by having the shardler for each processor examine the ready queue and select a process to execute. So if we have multiple processes trying to access and update a common data structure, like ready queue, the shardler must be programmed carefully. We must ensure that two separate processors do not choose to schedule the same process, and that processes are not lost from the queue. Virtually all modern operating systems support symmetric multiprocessor, including Windows, Linux, and Mac OS X. So, Section 2, Processor Affinity. Consider what happens to cache memory when a process has been running on a specific processor. The data most recently accessed by the process populated the cache for the processor. As a result, successive memory accesses by the process are often satisfied in cache memory. Now consider what happens if the process migrates to another processor. The contents of cache memory must be invalidated for the first processor, and the cache for the second processor must be repopulated. Because of the high cost of invalidating and repopulating caches, most symmetric multiprocessing systems try to avoid migration of processes from one processor to another, and instead attempt to keep a process running on the same processor. This is known as processor affinity. That is, a process has an affinity for the processor on which it is currently